Okay, the next speaker of this session is Soner Albayrak from Middle East Technical University.
Thank you so much. Let's see. Okay. Oopsie doopsie. So, nasıl ileri? Yeah, okay. All right. Okay. So today I'll be talking. How is the sound, by the way? Good. Okay. All right. So I'll be talking about a paper I wrote a few years ago. Um, it's basically applying some flat space knowledge regarding the unitarity and unitarity's implications, like optical theorem, to the cosmological setting. Now, let's start with what we know. Now, we know that unitarity of the integrant, we know that in FRW cosmologies, if we restrict to scalar theories, there is a universality of the integrants. I'll expand on that in a second, but we know there's something about the integration that if some factors come universally, which actually is expected because they represent only the kinematic information about the theories. We know that that universal part of the integrand of the wave function coefficients in FRW backgrounds is actually related to a graph in graph theory, which can be computed just using some rule-based algorithmic methods. And we also know that those graphs are related to something called cosmological polytope. Now, there are some papers about this, actually, which were initiated by the famous paper of Benincasa and Imane Arkani Hamed, titled Wave Function of the Universe. Maybe you know it. We also know that the unitarity of time evolution has some implications, like the optical theorem. And in cosmology, we also have something called cosmological optical theorem. And with all this knowledge, we are basically asking, can we find some relation between perturbative unitarity of time evolution in FRW background and purely mathematical tools in positive geometry? So that's the question we are trying to understand. Okay. So my outline will be, it's actually most of just reviews. Do I have a pointer? I guess not, it's fine. So it's mostly about reviews. I'll first review the universality of the scalar theories in FRW cosmology. I'll talk about the cosmological polytopes, and I review the unitarity in cosmology and the problems associated with that. And I'll review the cosmological optical theorem and problems associated with that. And finally, I will introduce something called optical polytope, which basically solve all these problems. Right. Let's see. So just take a scalar theory with polynomial interaction. Right here, let's look at the red expression right now. It's just some arbitrary scalar theory in arbitrary background. It's polynomial interaction. Now, if we focus on F, and I also assume a arbitrary coupling with the richest scalar, so chi is my coupling coefficient over there. And if we focus on FRW cosmologies, just restrict the metric to a simple one and apply a conformal transformation, this general form actually becomes quite simple, right? And we know that under a Weyler scaling, correlation functions between the original and final theories can be related by this green expression. Now, in principle, and here it's the expectation value of 1 is just schematic representation of the partition function. In principle, the partition function might change if you have Weyl anomaly. So I'll restrict the theories where there is no Weyl anomaly. Okay, that means with that condition given, my correlation function FRW computed by the action S, this thing, is equivalent to a correlation function in a flat space computed with the action S prime, where S prime is given like this. So this is nothing, this is already something very basic. We all know with FRW backgrounds are conformally related to half planes, flat half planes. So there is nothing fancy going on here. The only issue here is that, not an issue, but in this flat space theory, the mass and coupling constants are time dependent. Here, eta is the conformal time, which is expected. And the expression of m eta, oh, there is no pointer, is related to this A and chi and space-time dimension D over there like this, as you can see. And in fact, if in some special values of chi and in special dimensions D, you can have conformally coupled scalars as well, right? So it's well-studied simple theories. If you just consider conformally coupled scalar in ADS or DS, like 5 to the 6 in ADS4 or 5 to the 3 in ADS3 and so on, in that cases, this M square would be eta independent. But we're going to restrict to general theories for now. So they are time dependent, right? Now, we can extend this identification. So we identify the correlation functions here, computed with S and S prime. We can extend that to wave function coefficients as well. As a reminder, when I say wave function coefficient, we all know psi, quantum wave function, right? It appears in the computational expectation values in the Bond rule. And the psi n, the wave function coefficients, are basically like cumulants of the expansion of psi, right? These coefficients psi n. And you can actually find the relation between psi n and correlation functions. The relation between wave function coefficients and correlation functions are very similar to relation between moments and cumulants. You can compute them using the Bell polynomials, right? So if you know 2-point function and 3-point, if you know 2-point correlation function and 3-point correlation function, for instance, you can compute the second and third wave function coefficients psi 2 prime and psi 3 prime and so on. So it's really easy to go back and forth between them, assuming I am working around the Gaussian fixed point, meaning I'm working with the perturbative theory. Okay, so throughout the talk, I am working around free theories. So these are all applicable for weakly coupled theories. Good. Now, as a summary, if I want to compute the wave function coefficients of a cosmological model on FRW background, I can instead just use this half-plane flat space scalar theories with polynomial interactions using this S prime action. Okay, so let's focus on this for a second. Now here, the blue one is the Feynman diagram in the half plane. Time flows upward. So I have the boundary eta is equal to 0 is the current time. Actually, it's the boundary time, let me say it that way. It starts at eta is equal to minus infinity, right? And I'm trying to compute the wave function coefficient at the boundary. Now, I can give a bunch of reasons why I would be interested in that. Right? The simplest example would be the computation of correlation functions at the recombination time, which is the boundary of the de Sitter phase of the inflation. But this is one motivation. So let's stick to general case. Now, we can work in the, in the boundary directions, I can just take the Fourier transform and stick to momentum coordinates, since I have translational invariance for the boundary directions. Eta, let's keep it like that. So I work in the P eta space. Now, you can actually show that the form of wave function coefficient takes this form. It's basically some bunch of integrals which you can obtain taking a Laplace transform in Euclidean signature or half Fourier transform in the Lorentzi signature. It's related to a universal integrand here in the square. Now, that should make sense because that carries basically all the kinematic information. All dynamic information, theory-dependent part, is residing on this lambda tilde. Okay, now let me be fast actually. So that psi tilde is basically the universal integral which appears for any theory. It's independent of the coupling coefficients. It basically carries the kinematic information. And it's actually straightforward to compute. But one nice thing about that is its form is such that we only care for the sum of energies that enter to a vertex. It has additive condition. Meaning, for instance, these two Feynman diagrams are basically giving the same universal integrand in the computation. And that means instead of working with the Feynman diagrams, we can work with the chains, graphs of the Feynman diagrams, because they carry the same information. Now, these chains are actually simple. Let me give you one example. Like this first chain, for instance, it can be related to a 4-point Feynman diagram, 5-point Feynman diagram, and so on. Doesn't matter as long as you have this topology. So you only care for the topology of the chain. And they are computable. They're easy to compute. And you might say, okay, since we can directly compute them, what is the catch here? Like, why should I care for them? The thing is that these graphs can actually be related to some polytopes, some positive geometrical objects in some abstract projective space. And okay, let me skip this part for a second. Or let me quickly say that. Now, again, so you can basically relate these graphs to some abstract objects, geometric objects. Basically, like this first one, for instance, it's necessary for a 4-point tree-level Feynman diagram. It's related to a triangle in a 2-dimensional projective space Or the second chain can be shown to be like the loop diagram for a 4-point Feynman diagram. It's basically a convex hull of two triangles in three-dimensional projected space and so on. These are called polytopes. And we can make this connection between them. But the question is simple, like why should we care? Okay, let me go back. So we can make this connection. Mathematically speaking, these polytopes has some associated canonical form. And the canonical form of that polytope gives precisely the universal integrand of the wave function coefficient. So for any within diagram, for any FRW, for any scalar theory with polynomial interaction on FRW background, you can compute the canonical form of an associated object, cosmological polytope, and that will be equivalent to that integral. But that doesn't necessarily make sense. Like, why should we care for them, right? Let me skip this. Why should we care for them? Now, for computational reasons, it doesn't simplify anything. Okay, you can just compute and just take the integrals. You don't need any of this. The advantage, as we will see, is that it will give an unambiguous and unique way to make all computation perturbative unitary. Because as you can see, as we will discuss in a second, I still have time, as we will discuss in a second, it's not obvious, a priori obvious, how to make the time evolution unitary in cosmology, but this will give a unique way to make all computations unitary. So for that, let me review unitarity in cosmology. So we know that the standard one in Schrödinger's equation, you have a time evolution operator U. It evolves with respect to a Hamiltonian, right? It's a self-adjoint operator. And you just solve it. The formal solution is just time series time ordered operator acting on some exponential. You can derive this using Volterra's integral equation, right? Now, if we consider this U hat on a FRW background, like, or maybe DS, something like this, doesn't matter, with some Bunch-Davis vacuum, we clearly need some I epsilon prescription, right? This is not well defined as a function. It's actually well defined as a distribution. So we need I epsilon prescription. In flat space, we can very quickly do this. Just deform the integration contour and everything will be fine. In the cosmological setting, that's not possible because if you do that, then the time evolution operator is no longer unitary. And that's the result of the fact that there is no time reflection symmetry for cosmology. In flat space, when you compute scattering amplitudes, you usually take initial time to -infinity, final time to +infinity, to compute the scattering amplitude, the S matrix, and you have the time reversal symmetry. So you can deform the integration contour and still respect unitarity. In cosmology, you work with half plane, right? So your cosmological, the conformal time goes from -infinity to 0. So if you try to deform the integration contour in the same way, analogous to flat space, then your time evolution operator is no longer unitary. That's the problem. Now, one option would be not change the integration path, but to regularize the Hamiltonian, right? You can try to regularize the Hamiltonian such that time evolution operator is still well defined as a function. But then the problem is, in which way should I regularize the Hamiltonian? Now, there is no longer an unambiguous, unique way to make things consistent with unitarity. Okay, that's the issue, actually. We expect causality should have some implications that we cannot choose any regularization of Hamiltonian, but it's not well known as of today. So we are trying to find a way. Now, as summary, we have the wave function of the universe. It just acts on, you just take the time evolution operator, act Bunch-Davis vacuum, right? And compute this inner product. It gives you the wave function of universe. We know that it's well defined as a generalized function. So generalized functions distributions are basically defined at the boundary of the analyticity of ordinary functions, right? So you have an ordinary function. It is a region in which it's holomorphic and well defined. If you take that function to the boundary of the holomorphicity of the function, it becomes a distribution. And the usual procedure to take a function to its boundary is epsilon prescription, what Feynman does. But we cannot just do that as we do it flat space. But if you instead use the polytopic representation of these integrations, then there is actually a unique way, unique epsilon prescription, which makes everything unitary. That's the idea. Okay. And that is because computing psi through using polytopes has a natural epsilon prescription. Because the idea here was that we have a graph first, we need to compute a graph, which is associated with a polytope, which has a canonical form, right? So you find a canonical form, which gives you the universal integral, then you integrate it against the Laplace transform of the coupling coefficients to obtain the wave function coefficient. But along this step, the canonical form has a contour representation, which has an epsilon prescription that is uniquely fixed by the conditions of the polytope. And what are they? So by the definition of polytopes, their orientation has to be preserved. In their computation, like there's some technical conditions, like y needs to be internal point of the polytope, there cannot be any pause on integration contours and so on. Long story short, there is an unambiguous unique way to insert epsilon. So you cannot just choose signs as you want. Okay, like for instance, this sign needs to be minus in terms of epsilon and so on. So that's basically the upshot. So I'm going to be a little bit quick. That was an example here, but it's not important. Another advantage of this polytope interpretation is polytopic way of computation is that, as we will see, it will actually help us derive the correct optical theorem in cosmology. So for that, let me review the optical theorem. Okay. Actually, even before that, let me review the optical theorem in flat space, right? So in flat space, we know that the imaginary part of a scattering amplitude is related to products of scattering amplitudes like this. So X is an intermediate step. So if you have some scattering from initial state to final state, then for any intermediate step, you can basically compute two scattering amplitudes, take complex conjugation of one of them, take the product, integrate that will be related to the imaginary part of the scattering amplitude. That's a non-perturbative statement. It's a result of unitarity. Okay, and it gives constraints on sums of Feynman diagrams. It gives constraints at the level of amplitude. It doesn't give constraint at the level of Feynman diagram. It gives constraint at the level of amplitude. Okay, so that's a very powerful, just direct result of unitarity. Now, there are different ways to see why it's like that. Historically, Katkowski basically showed that this is related to discontinuity across lambda surface of the Feynman propagator, because if you take the scattering amplitude S matrix and analyze its analyticity, you would find some discontinuities, and that discontinuities, like computing the value of discontinuity of scattering amplitude, is actually what you get from the optical theorem. And Hooft and Weltman actually even generalized this. They obtained this covariant cutting rule. You don't even need unitarity for that, but it is important. Well, you need unitarity, but the upshot is that you have this algebraic relation for any theory you want, right? You can basically relate a property of the amplitude to some of the so-called cuts. For unitary theories, that property becomes imaginary part of the amplitude. So it's well established that by taking cuts of the amplitude, you can compute the imaginary part. That's the optical theorem. And by taking cuts, I mean replacing the Feynman propagators with Weidmann functions. So in flat space, that's well known. Basically, Weidmann function is just computation of two-point functions without time ordering. As you know, Feynman propagators, you need the time ordering. So in Weidmann function, you don't need that. So if you do the replacement, if you replace the Feynman propagator with Weidmann propagator, that's called being cut. And if you do all of these cuts in all possible permutations and sum them, that gives you the imaginary part of the amplitude. And actually, by using these cuts, you can relate loop diagrams to tree-level diagrams. So basically, optical theorem allows you to compute loop-level diagrams just using tree-level information. Now, there were some papers which try to apply the same methods in the case of cosmology. There were some bunch of results. Let me quickly go over them. Actually, let me quickly skip them. But the long story short is that the usual methods of the flat space doesn't work in cosmology. Because if you work with the Bunch-Davis vacuum, then the discontinuities of the cosmological wave functions are not in the physical region. the discontinuities of the cosmological wave functions appear in regions where some of the norms of the momenta are zero, which is not in the physical region. That's unlike the flat space case. In flat space case, we could probe the discontinuities of the scattering amplitude working with the physically accessible momenta. You cannot do that in cosmology. So what can you do? You can try to get some relations like this. There are papers about it, but they are not that useful. First of all, when you take the flat space limit, they become trivial. They just give you 0 is equal to 0. No useful information. Secondly, they miss the distributional contributions. So these relations are all distributional. They shouldn't be functional relations. And there's important information in the distributional parts. They missed them and they couldn't find, and there were also thirdly, a bunch of different expressions for the same cosmological optical theorem. So they were equivalent but different expressions. And they were trying to show why they're equivalent. They couldn't. So as a summary, since I'm running out of time, I guess I only have 8 minutes left. So basically, you can, as a summary, you can show that by using this, by associating this computation with a polytope, firstly, you can compute the cosmological optical theorem in full parts. You also get distribution contributions. Secondly, when you take the flat space, you don't get 0 is equal to 0. You precisely get the flat space cosmological flat space optical theorem. Thirdly, the different optical theorems in literature turn out to be associated with different triangulation of the polytope. So when I say triangulation, I mean something like this. Let's look at this quadrilateral. Okay, square. So let's say you want to compute this quadrilateral. There are two different ways to triangulate it, the green way and the blue way, right? If you were to do that, this will actually basically give you two different equations. Now you do the math, basically. In other words, it's like in the graph sense, that's equivalent to doing different contour integrations for the same computation. So they will give you different results, but they're actually all equivalent. So we basically showed that all the results in the literature are basically the same thing. They all appear from these different triangulations of the polytope in higher order abstract space. So let's go back here. Let's see. Okay. Right. So to show this, to show all of this, we introduced something called optical polytope. That's similar to cosmological polytope. It's actually a little bit uglier. Again, the details are not important. You basically introduce some object which has an associated positive geometry. You compute this object, and from that object, you can derive cosmological optical theorem. You can show that all these different methods I've been referring to are just different triangulations. Okay. Let's. I have 3 minutes left. It's 4:57. Anything else I want to add? Okay. Yeah, I think that's it. Yeah, summary. Let me summarize. Okay. So for any polynomial interacting scalar theory in FRW background, we already knew that there are these universal integrands. Again, that's nothing novel about this. It's just a kinematic part of the computation. But the thing was that those universal kinematic parts can be associated with a graph in graph language, and all those graphs can be associated with a polytope in a projective high dimensional abstract projective space. And the canonical form of those polytopes, some mathematical expression associated with these geometries, are equal to the wave function coefficients. And even though you can compute those wave function coefficients just by taking the integrals, it's not too hard integrals. Okay, you can just do the computation. I mean, not too easy, but not too hard. But the advantage of using polytopes was that, firstly, they bring an unambiguous, unique way to introduce I epsilon to make sure that the unitarity of time evolution is satisfied. Secondly, if you derive cosmological optical theorem using these polytopes, instead of just doing the ordinary computation, you realize that firstly, you can get the missing contributions, these distribution parts. Secondly, you get the correct flat space, which was absent in literature. And thirdly, you realize that different optical theorems in literature are just the same thing, because if you define this optical polytope and triangulate it differently, you get all these different cosmological optical theorems. So that would be the summary. And there are some open directions, right? Yeah, so we don't know what's the role of causality in all this discussion. I mean, we discussed this. We think like you should put some constraints as well, just like unit theta, but we don't know the relation fully well. We can try to generalize this from just the integrand to full integrals. That's an open question. Of course, we can try to extend this to loops. You know, the R-Steinman-like relations, we don't know. And finally, you can try to maybe generalize the form of interactions like derivative interactions. What would be the case then? These are all open questions. Okay, thank you so much for your time.